So we had finished up talking about sort of this idea of providing point estimates, which is what we typically and historically do with our descriptive statistics and our inferential statistics. But important to recognize that anytime we calculate a point estimate, there's going to be some uncertainty around that, right? Our point estimates are never the single one corresponding population parameter. And so what it would be nice to do, again, is get some level of the extent to which our measurements are precise, right? So here's my best guess, but how much error am I expecting to surround that point estimate? And this is where our interval estimates come in, right? We talk about our confidence intervals here, providing an index of precision of our instruments, as well as the range of plausible values for a population parameter based on the available data, okay? Remember, the way we go through and calculate these, and the way we interpret these, this is always our hedge. This is always our caveat, right? This is always what we contextualize this based on the data that we have. This is our best guess. This is the level of precision that we can expect. But as we talked about before, there's important reasons why we have that hedge, right? So we talked about the confidence interval. Here, this is just a confidence interval around a mean, right? So we're trying to estimate some mean value in the population based on our sample. So we've got our point estimate, our mean, our confidence level that we've calculated, and then this is our interval estimate, okay? Formal interpretation of our confidence interval, because these are mathematically, statistically based on a frequentist approach. We're saying the technical interpretation of our confidence intervals is going to be if we were to do this over and over and over and over and over and over again across repeated trials, theoretically an infinite number of trials, the proportion of intervals that we would calculate from each one of those replications that will actually capture the true population parameter. Okay. This is kind of wonky, but important to recognize because it helps understand why it's incorrect to assert that there's a 95% chance that the confidence interval contains the true parameter. Or even worse, that this interval will capture the population parameter 95% of the time. Okay? Someone tell me why we can't interpret, or we shouldn't be interpreting confidence intervals this way. What do you think, Stephanie?
Because the parameter is a constant, it's not a variable. So there's a true value, it will always be.
Right. And so you're exactly right. So if we're thinking about actually how confidence intervals are calculated and what they represent, again, we see this is the true value, right? This is the population mean. And we calculate, if we were to calculate with replication, right? A great number of different samples, and for each one of those samples we would calculate a point estimate of the mean and a confidence interval. The way we go about this, we would expect with a given interval based on this process, right? The interpretation is about the process, not about the given interval. And what we would find is that over many different replications, 95% of the intervals, or approximately 95% of the intervals that we calculated would capture the population parameter. But for any individual interval that we've calculated, right? And is anybody planning on running an infinite number of replications for any study? No, right? We've just got the one that we did, and we don't know whether we captured the population parameter or not, right? And so we could be here, hopefully, we're in one of these, but we could be out here, right? And so if we're out here, we can't say that 95% of the time this interval captures the population parameter, because it doesn't. It's never going to capture the population parameter, right? And particularly if you say that 95% of the time the true population parameter will fall between X and Y, that's particularly egregious, because you're literally saying that the parameter of interest is a variable, right? That it's sort of hanging out, and sometimes it jumps in here and sometimes it jumps out there, and that's not the case, right? And so wanting you all to be very specific, and I'm going to beat you over the head about this, in your interpretation of your confidence intervals. One, to make sure they're correct, and two, to make sure that you're incorporating these and providing meaningful interpretations about these interval estimates, okay? Again, coverage probability is property of the long sequence of intervals, right? The way we calculate confidence intervals, that 95% piece, that's about the process, right? It's not about any one individual interval. And again, we're always saying, based on the data that we have available. Now, our data might be crap, okay? And it doesn't matter how many intervals we calculate, given our method, they're never going to capture the population parameter because our methods are crap. But hopefully we don't have crap methods and can expect that at least some high proportion of potential intervals that would be calculated are going to get a hold of the parameter of interest, right? So again, oh yeah.
So then, what was that specific confidence interval that we calculated for this specific set of data? Like, what does it tell us about our star data?
It tells us about, assuming that we've done a reasonable job of trying to capture sort of whatever it is that we're trying to capture, it gives us our level of precision, okay? And this is the uncertainty that comes with statistics, right? We think, oh, it's numbers, and we just calculate it, and this is the answer. Couldn't be farther from the truth, right? Because even if you're doing everything right? Even if you have the best epidemiological random survey, most of those, particularly if the survey is pretty big, you're probably going to be pretty precise, right? But if we do this over and over and over and over again, eventually we're going to hit a parameter or an interval estimate that doesn't capture our true effect, right? We hope it does, right? We just don't know, and so we have to be very careful about how we talk about these, right? And so, some different conceptual interpretations. Confidence interval representing a range of plausible values for whatever it is we're looking for, given the available data, right? Okay. And again, we're just saying, hey, we don't know, right? But given the data we have available to us, this is the upper and lower limit that seems plausible based on the process that we've gone through, right? Because research is a process, right? We're not sort of identifying. If we had access to the whole population, we just say, yep, that's the mean, because it is, right? We don't, but we don't have that level of accuracy, and so we say we can interpret our confidence intervals as a range of plausible values. I like this a great deal, and the corollary to that being the values falling outside of the interval are reasonably implausible. Not impossible, right? Because we never know. We might have gotten a weird, wonky interval, right, due to random chance or poor methods. We're not saying that values outside can occur. We're just saying that they're implausible based on the data that we've collected, okay? And this starts to become important if we're thinking about trying to think of an experimental. So if you say, from like an experimental time, say you're looking at reaction time, right? And you want to see the impact of alcohol on reaction time to some sort of task, right? And so you get people boozed up and you have them go through and do some reaction times. And then you say, all right, so based on this level of alcohol in someone's system, this is the level, this is the delay that we would expect in reaction time. Based on the available data, sort of this to this would be our best guess in terms of what the actual millisecond delay is in terms of stuff, right? And so we're saying that if on average, people with this level of alcohol in their system are likely to have anywhere from this to this level of delay, right? So something that actually takes that and takes it out of an abstraction and actually puts it into an applied thing, because this can start to be important for either theory or practice or things along those lines, right? So thinking about these as actual literal things that have real meaning within your research or out there in the real world. We could also say observed data are compatible with values falling within the interval, but relatively incompatible with values falling outside the interval. That's saying, like, here's my mean. I'm not saying that this is the end-all be-all mean, but I'm saying that means falling somewhere within this interval, based on these data, would be considered plausible. Stuff falling outside of that would be relatively implausible. Okay, let's say you're running a study, or you're looking at a meta-analysis, right? and it's looking at the meta-analyses of the relation between X and Y, right? And you see that aggregated across bunch of studies, we see that this is our best guess of the estimate of this relation sort of based on the data available, right? So you've got this, let's say it's a correlation, but if it's a good meta-analysis is going to say this is a level of imprecision around there, right? So meta-analysis, best guess of the correlation is 0.4, and I get a correlation of 0.25, right, in my study. And I'm kind of bummed about that because I was hoping it was going to be 0.4. Now, is that outside, is this something that would be expected or not expected? That starts to get kind of complicated, but what we can do is not just say, oh, if it's 0.4 nothing, looking at the interval estimate around that effect size to see, are we close, are we in there? Is this reasonable, or is my study looking like something that's not typical of the larger research? Okay. So we like that one. Lower limit of the interval provides a reasonable lower bound estimate of the parameter. Upper limit, reasonable upper bound parameter, right? Sort of giving some tolerances here. We like that. Margin of error reflects the largest error of estimation likely to be made based on the available data. Our margin of error, this is going to be your, when you're calculating your confidence interval, whatever your, like say 95, right? Right, and so this is going to be your, we're using a z-table, 1.96 times whatever your standard error is, right? This is going to give you your margin of error. This is going to be your mean plus or minus whatever this value is. That plus or minus is your margin of error, right? And so if we have, say, a 95% interval is 100 plus or minus 15, right? Our interval is going to go from 85 to 115, right? And if that was our interval, we would say that this margin of error of 15 points represents the largest error in our estimation that we're likely to make based on these data, right? So we're saying that we're expecting our point estimate that we've found, right, in our study to probably be, is probably going to be no more than 15 points above or below the actual mean, right? So again, here instead of working with upper and lower limits, we're working with this margin of error, the plus or minus here. And so that's good. And here we can be 95% confidence that our interval includes the mean. Cumming and Finch give this as a viable interpretation. I don't like it, right? I don't want you to use it. I want you to be thinking about these in actual applied parameter or in applied terms, thinking about this. Technically, you could say, well, if we're saying 95% confident in that over multiple replications, that 95% of our intervals are going to fall within, are going to capture the true population parameter, then yeah, you're right. But what we tend to do is interpret this incorrectly, as in there's a 95% chance that this interval captures the population parameter, and so I don't like that, okay? So use one of these or some other derivative that you don't, and not a cut and paste, right? I want you guys to be thinking about how to go through and incorporate these, but again, mix this up. Use some different interpretations that'll strengthen your understanding of how to go through and apply these. Also, don't give me a frequentist approach where say over an infinite number of replications. As soon as you start talking about infinite number of replications in a study or a paper that you try and publish, your reviewers' eyes are going to glaze over and they're going to say, they're going to send it back to you and tell you to give it another try. Okay? All right. There's a review of the last 20 minutes of our last class, but this is just incredibly important, something that's going to you're going to be doing. Assume for any assignment, unless I tell you don't calculate a confidence interval, expect me to be expecting the confidence interval to be included with your stuff, okay? Just because I don't say it doesn't mean you don't need to do it, because if you don't put it in there, I'll probably write confidence interval, question mark, circle, yellow highlighter, red, right? So just want to make sure people are clear on this, okay? So again, I think just a color in writing, researcher routinely reports 95% confidence intervals can, over a lifetime, expect that about 95% of these intervals will capture the estimated parameter, right? I mean, just to kind of put this in practical terms, right? To take it out of the abstraction. I don't want this to be just numbers that you're calculating for the hey-ho heck of it to get a grade, right? There's better things for you to be doing with your time. We want you to be thinking about these in practical terms. Go on so you can apply it down the road, okay? Strengths of our interval estimation, providing both a point estimate and an estimate of the probable error in our prediction. How accurate are we, right? With our interval estimates, we're saying, okay, how much, what's the parameters, what are the bounds versus is this equal to 0, right? In the previous slide we had, you know, exercising 5 times a week has been shown to impact increased longevity, right? Well, fine, right? But actually I'm probably more interested in how much. Like, how much does that increase longevity? Is it a lot? Is it little? Our statistical tests generally say, does it increase it by 0, right? Well, that's often not interesting. More interesting is by how much. Our confidence intervals give us this. Our confidence intervals give us exact same information as our inferential statistics, okay? Do not, everybody look at me in the eye, okay? This is the forward thinking. When we get into our t-tests and our things, right? Alex is intense about this, right? Do not say, I found a significant t-test, and I also found my confidence interval doesn't include 0. That gives me more evidence for that my t-test is correct. T-test your confidence interval based on the same amount of information. It's not adding to it. But what it is doing is giving a fuller degree of information than your t-tests, your correlations, things along those lines, right? And so the argument being that with our interval estimation, we actually don't need our actual hypothesis tests unless we're really hard up to get a p-value, which we often are because that's the standard for publication and things like that. But what I can do is if I run a confidence interval around a mean, and that interval doesn't contain 0, I don't need to run a hypothesis test because I already know it's going to be statistically reliable, right? And so if our interval contains some reference value, then it's interpreted as failing to reject that null hypothesis, right? Because if we say we're looking at the difference between 2 means, and our point estimate of the difference between those 2 means is 5, but our 95% confidence interval contains 0, well, it seems like, based on our interpretation, 0 or no difference is a plausible value based on the interval that we've calculated, and so then we would fail to reject the null hypothesis in this, right? But if it doesn't, then it's interpreted as evidence for statistically significant or statistically reliable difference. So our confidence intervals are giving us everything that we would want to get, probably from a practical standpoint from our inferential tests, but it's giving us some additional information above and beyond that. But do not tell me that you have more evidence for your hypotheses because your confidence interval told you the same thing as your inferential test. It's the same thing, okay? All right, also, confidence intervals, more accurate, meaningful perspective on observed effects within the literature. Again, if we start saying, well, Perry et al. Found a mean difference of 20, and I found a mean difference of 25, and so my study is better than Perry et al. Well, probably not. If we're thinking about things in terms of precision and then we've got some error in both of these estimates, it's probably pretty much the same thing, okay? So again, going back to that Wilkinson paper, talking about confidence intervals combining information, location, precision, in general the best reporting strategy for communicating information about our research, okay? Yeah, Henry.
I guess the part about the 0 part, I don't understand what the 0 is.
We'll get to that later. Don't worry about that right now. In terms of this, in terms of the confidence interval,
Like, the question, it says like, is this equal to 0? What does that refer
Oh.
to?
so our null hypothesis test, and again, we'll get into this when we get into our hypothesis test later on today. So bring this back up when we get to that, and we'll cover it then. Okay, yeah. Basically, anytime we're running a statistical test, we're almost always testing whether or not something is 0, right? If I'm running a correlation, right, I'm saying, is the relation between X and Y 0? Right? Well, I don't know if that's a meaningful, it's often not a meaningful question, right? If it's exactly 0, right? And we'll talk about ways in which that starts to become less interesting than, well, I know it's not 0, but how much is it not 0, right? What are the range of reasonable estimates for the likely relation between X and Y? Yeah.
So why do you think, like, this isn't taught in, well, like, because in my experience, I've taken a couple statistics classes, I wasn't taught this way. I was taught that the 95% confident is okay. Why do you think that, people aren't recognizing that or teaching that?
I don't know. I don't know who your informal instructors are, whether or not they watch YouTube.
Not good.
Right? It doesn't. It's more difficult,
Okay.
right? And it forces you to think about. I was thinking about this today. Okay, we're gonna drop a parable on you, right? Right? So like this idea of like going through, and particularly with statistics, I'm assuming that you all, because you're in a doctoral program, that you will be using this and have some at least general interest, and that you're in this program and knowing actually what this stuff is about, right? What we're working for here, and my hope for you, is that you get an actual useful and applied understanding of these tools, as opposed to these are just the motions I go through, right? So we've got two people. So we've got Katie and we've got me, right? We're both familiar with the concept of hygiene, right? But Katie knows about hygiene because she understands what hygiene is about and why hygiene is important, things like that. I know hygiene as this is the series of steps that I go through each day in order to maintain my hygiene, right? So in circumstances, I get up every morning and I take a shower and I brush my teeth, and that's my hygiene, right? I'm probably gonna be okay a lot of the time, but sometimes I'm not. Sometimes I'm gonna go out and I'm gonna get cruddy, right? And I need to take a shower because I'm smelly, but I don't recognize that because these are the steps I take to engage in hygiene, right? Or maybe I'm going out and I've been drinking coffee all day. I'm gonna be breathing on people. I need to brush my teeth, even though it's the middle of the day, but I don't, because I brush my teeth in the morning. Those are the rules to follow for hygiene, right? Katie, on the other hand, is much better at hygiene, understands the purpose of hygiene, why we use hygiene, ins and outs of hygiene, is able to apply rules of hygiene much more flexibly and much more effectively, right? It's the same stuff with, like, this is like, oh, these are the steps I'm gonna follow to calculate this test, irrespective of anything else that might be going on. Ends up to bad inferences, bad science, things along those lines, right? If I'm teaching undergraduates, it's much easier to say, look at this value. If it's above 0.5, it's statistically significant. If it's below 0.5, it's not statistically significant, and just leave it at that. And to be fair, at an undergraduate level, you may not need a whole lot more than that. But I have much higher hopes for you all. Thinking about this class is giving you a set of tools and a set of applied skills, right? Being able to use this and think about things flexibly. I've got 7 different options for when I might shower today. Which one makes the best sense given the situation that I've been confronted with, okay? So, one, it's hard, and then we don't do it, and then so people don't report this type of stuff. But I think we are starting to see a shift in the literature where you are starting to see journals that will require you to provide this stuff, will require you to provide effect sizes. And I think that's really 2 things. One, if you're forced to do it for publication, people will do it. And 2, if you're trained to do it and beaten over the head with it for a full-on year, hopefully some of that stuff will stick and you'll start thinking about this in terms of your own research. Cool. All right, yeah.
So in what kind of scenario do we use 90% confidence interval against 95 against 99%? So which one would be?
It's going to be an area specific thing. For psychology, for psychological science, 95 is typically the standard, right?
So every field has their own set of standard.
95 is probably going to be typically what people are looking at, right? But there's going to be circumstances if I calculate a 99% confidence interval, is my 99% confidence interval going to be wider or narrower than a 95? Wider, right? Because I've increased, I'm hedging my bets, right? I'm going to say, oh, I want to go from 95 to 99, so my interval is going to be wider because it's going to catch more of this stuff, right? If my interval is wider, more of these intervals are going to capture the population parameter than not. If I say a 90% confidence interval, it's going to start to get narrower, right? And so, but depending on what you're trying to do, let's say I'm developing a medication and I'm running a test on whether or not this medication is going to kill somebody, right? I want to be much more precise on that, right? Than I don't know. Here's something that is just generally good and easy to employ, like reading books, right? Reading books is not a whole lot of cost to that, so it maybe sort of use a different confidence band for that. So it sort of depends on sort of the consequences of getting it wrong versus getting it right type of thing. But in general, for what we do is we'll switch back. I mean, we'll primarily calculate 95% confidence intervals, unless I'm trying to trick you and make sure you're paying attention and tell you to calculate a 99% confidence interval, and sort of aside from that. Okay. Other questions? All right. I will be watching you again, wanting you to include confidence interval estimates. I want you to interpret them appropriately, and you will continue to get points taken off if you don't do that correctly. So again, look at feedback you're getting from Candace, from myself, to make sure you're on point with that stuff. Okay? So, calculation of our confidence intervals, 3 pieces of information, and so this is for any confidence interval, but we're just talking about confidence interval on the mean here. We've got our sample mean, this is our point estimate, our standard error, and our z-value, and eventually t-value for chosen degree of precision. Standard error, we're going to spend a lot of time today introducing standard error, talking about standard error. Standard error, roughly for right now, this is an index of how much difference, how much error is expected from one replication sample to the next. Okay? Going back to our example of average height of students at the University of Wyoming. Okay? If I go through and I calculate and I go through and I randomly gather samples of 50 students and look at the average of their height, over replication, then I do this over and over and over again, my standard error is telling me how much difference I'm going to be, how much variability I'm expecting from sample to sample. Okay, this is going to be thinking about this, and we'll get into this in the next lecture, as your standard deviation of your sampling distribution. Okay, so how much difference expected from one replication to the next? Alternatively, we can think about this as how well an individual mean expected to estimate the actual population mean. Okay? If my standard error is large, I calculate a sample mean, and I've got a large standard of error, and a large standard error. Do I have a lot of faith that that mean is a reasonable reflection of the population mean, or am I more worried about this? What do you think, Katie? More worried about it, right? Because if I've got a large standard error, say I've got a standard error of 6 inches, right? I'm expecting in my estimation of the average height of students on the UW campus that each one of my samples could jump on average from about 6 inches. That's a lot if we're talking about height, right? Say, oh, the average is 5 5'6" versus 6 foot, right? I mean, that's a lot of jumping around, right? And so if with large standard errors, I don't know, I don't have a lot of confidence that the value that I've captured is actually a good or reasonable estimate, right? It's just really variable. We're going to calculate standard errors using measured standard deviation over the square root of your sample size, okay? So what are the primary influences on our standard error going to be here? Alex? I mean, what's going to happen if we start changing around these values?
The standard error will change, so.
Yeah.
This one, the n, so if the n gets bigger, the standard error will get smaller.
Perfect, okay. And what else? What else can we change with the standard error?
If the standard deviation is greater than the standard error.
Excellent, okay. And so wanting you guys to all be looking and thinking about with these ratios, everything we do is working with ratios. What happens if this gets smaller, that gets smaller? And so as we go through, and so in general, this is often something we can't do anything about, right? But this is. So as our samples get bigger and bigger and bigger, what happens to our standard error? It gets smaller, right? And we have a smaller standard error. That means, what about the precision of our sample? It's better, right? And so bigger samples mean more precision. Smaller standard errors, they mean tighter confidence intervals, and they mean bigger p-values because we have less error in the whole calculation, okay? So again, we'll talk a lot about standard errors. Standard, like, that will often be the answer to questions. Like, what happens to this if we screw that up? Yeah, well, it screws up your standard error, right? So I want you guys to get a good sense for conceptually what the standard error is. Yeah, Stephanie?
Are there general guidelines about what is considered a large standard error versus acceptable, or is it just our judgment?
No, your standard error is based on the units of whatever you're measuring. And so there's no way to say, I mean, here's a standard error of 50,000. That might be good or really terrible. I'm not sure, right? It's sort of like variance. I don't know. Or standard deviation, right? Like, I can't look at it and say, oh, this is a good standard error or not. But we'll talk about factors, design factors that start to help improve your standard error, and that's going to be more of a consideration than the absolute value. All right, so calculation of our confidence intervals. We've got our mean, our standard error, and then our, right now we're going to be working using our z-values for a degree of confidence, calculating a 90% confidence interval. We've got a z of 1.65, 95%, 1.96, 99, 2.58. Can someone tell me where I got these values from? Yes, absolutely, Alex. But tell me, what do these values correspond to? So what do these z scores represent, or where these boundaries fall? Yeah. So z of 1.96, I'm almost 2 standard deviations away from the mean, right? But where am I getting that 95% interval piece of things?
What column is the mean?
Yeah, what is it?
The mean to z of 45, or 0.45, so it's just a, so
Okay.
if you're 90,
If you're 90.
on either side, it'll be 45 on
Right,
each
right, right.
side of the mean.
Okay.
So,
So talking about the body of the distribution, what are we typically interested though in it with calculating these intervals? The tails, right? And so if we have our our normal distribution here, okay, and we go through, and this is 1.96, 1.96. Sam, how much is what percentage of what proportion of the curve falls below 1.96 in the negative.
Sorry, but before we go, let's see.
Oh, yeah, no worries.
Might take a good moment.
Okay, if someone else has their Z table out, Angela, I see you got it.
What proportion?
Yeah, in the,
2.5%, so.
right. Nope, you're absolutely, 2.5%, right? And how much above 1.96? 2.5, right? What's 2.5 plus 2.5? 5, right? And if we take that from 100% of the distribution, we get 95% of the distribution, right? So 95% of our distribution falling between here, right? And these are just the bounds for the top 2.5%, the bottom 2.5%. Same thing, if we go out to 2.58, we've got, we're capturing 0.5% out here, 0.5% down here, right? 90, bring it in, 5%, 5%, and this is where these values are coming from, okay? So once we've got all of our values, then we're just taking our point estimate, plus or minus our level of confidence here, plus multiply that by our standard error. This gives us our margin of error, which we then use to calculate our confidence intervals. Okay. So, as an example, so we've got situation. We've got old librarian at our sort of establishment here has said, on average, books in the library are 20 years old. Okay, new librarian comes in wanting to get a better sense for what's going on with the age of the books. Samples 150 books, records a publication date. Mean age of the books in the sample is 23.8 years, with a variance of 67.5. Okay, so we've got a mean 23.8, and we've got a variance 67.5. Sample of 150. Okay, so we know that new librarian has gotten a decent sample of books, right? And he's calculated a point estimate for the population of books in the library, right? So our point estimate here is going to be 23.8. The question is, that's not perfect, right? He didn't calculate the age of all the books. This is just his point estimate of all of the age of all the books in the library, right? And so what it might be nice to do is get a sense for how precise this estimate is going to be, okay? And so we're going to calculate a confidence interval. Or well, I guess point estimate of the true age of the books is what? Sam? 23.5, right? We drew a sample from the population of books. This is our best guess as to what the actual population or the actual average of all of the books in the library is, right? Well, we know that's not going to be exactly right, okay? And so what we want to do is we want to calculate a 95% confidence interval for this. What's the first thing we need to do?
Just square root of, get the standard.
The standard error.
deviation.
Absolutely, right?
Yeah.
We want the oh, well,
We're
we
gonna
need
get
to,
the standard deviation. from
yeah,
that.
we can do that too.
One more.
Yeah. We'll do a shortcut. We can go 67.5 over what?
One.
Sample?
Just add
150. And then we do just take the square root of the whole thing. That's functionally equivalent, right? Threw a trick at you. I was like, variance instead of standard deviation, which are too fast for me. You got it anyway. All right. So what do we get as a standard error of the books here?
0.671.
What do we get?
0.67082.
0.678?
08.
670?
Yeah. Well, it's 08, so I don't know if you can round that to 1.
Okay, yeah. right, so here's our standard error. All right. Now what do we want to do? What's that? Okay, yeah, so what do we, do the confidence, the hottest new dance in nightclubs. All right. It's probably a bracket type thing. Right? All right, Lauren, what do we need for the confidence interval? The mean, right? 23.8 plus or minus what?
The 1.96.
1.96
Times
times standard error, 0.671. Oh, a little fun with statistics, George. All right, so what do we get? What do we get for our confidence interval here? What's our lower bound?
22.486.
22.48. And what's our upper limit?
25.114.
25.12.
Yeah, 114.
What's that?
114. So it can be one. So to be precise, it's 25.114.
Okay. 114, 25.11. We'll give it some rounding error there. And Rosie, I'm sorry, like I don't even know if you can see any of this stuff
I
behind
can't
that.
see any of that.
But it sounds like you got it under control over there, all right? But, so we've got our confidence interval here, upper and lower bound. So, someone give me an interpretation of our interval estimate here. Morgan? Can you give me an interpretation of our confidence interval here?
Not confidently. It's all right, I didn't even mean to make that. Sorry, that was bad.
That was awesome work.
That was terrible.
Glad we got this on video. It's live at the Met album here.
Okay, hold on, I'm sorry, I gotta take a look at it, because I can't see that far.
Oh,
I gotta look at my notes, I'm sorry. So. No, at this moment, I can't give one, I'm sorry.
give it a shot. Give it a shot. Because if you get it wrong, other people have got that wrong that way too. So.
Well, no, I don't need yours. I mean, I got my numbers, I just don't know how to interpret Denver.
Okay.
I guess.
That's all right. So, what's our point estimate?
23.8.
23.8. Okay. Do we think that this is? Are you willing to stake everything you own that this is the exact average age of every book in the library?
No.
Okay. So, we've calculated our confidence interval, and so how do we interpret our interval estimate?
We could be confident that if we picked all of our books, 95% of them and their ages would fall between this range.
Okay.
Would be, or they would, 95% of them would be this old.
Okay. So,
No.
not quite,
No,
but I think,
no, that's-
and I think, but this is good because this is, I think, where people start to get cranked up about.
This is the pace of cranked up.
Forget about the level of precision, right? Because someone's going to look at your confidence interval and see you calculated 95% confidence interval, right? I'm less worried about you getting that piece of 95% in based on the interval that we've gathered. What are these, or based on the information that we've gathered? What do these limits represent, Stephanie?
I'm sorry, can you repeat the question?
I said, based on the data that we've collected, what are these intervals, or what do these bounds represent?
The upper and lower limits of the possible true parameter.
Almost perfect, likely, or probable, not possible, right?
Oh.
Because the actual age of all the books in the library could fall outside of this, right? Maybe we just got a wonky interval, right? It's not impossible, but it's not likely, right? So we would say, based on the data that we've collected, our interval suggests that the actual population, or the actual mean age of books in the library range somewhere from 22.48 to an upper of 25. So we could take a look at this and say, based on the data we've collected, plausible estimates for the average age of books in the library range somewhere from 22.5 to 25.1 years. We could say that the largest error of estimation likely to be made from this is somewhere around 16 months. Okay. Where did I get 16 months? What's our margin of error here?
It's 1.314,
Okay.
so it's 16 months.
Yeah, right. So if we take a look at this value right here is going to be something around 1.3, right? So we could say, we'd also say we would expect that largest margin of error we would make around this is somewhere between 1.3 years, but you also did 16 months, right? Just as a way to demonstrate like how to take this and start sort of playing around with things so that it makes a reasonable, 1.3 years is kind of a weird thing. If you say 16 months, that's kind of maybe a better way to communicate that, right? We could also say, if I'm looking at this, right? Do we have reasonable level of precision here or not reasonable level of precision here? And again, thinking about our task at hand, which is identifying the average age of books, right? What's that? Yeah, it's not bad, right? Based on the data we've got, we've tacked it down within a little over a year, right? That's pretty good, right? So you might, if you were commenting on this, you say, it might suggest confidence interval indicates a reasonable level of precision in the estimate of the age of books in the library, right? So there's a lot of different ways that you would talk about this. I just want you to talk about this in a way that's not just a cut and paste across every single assignment that you turn into me, saying that the reasonable, plausible range for whatever it is we're looking at runs from here to here. Not that you can't use that, but just wanting you to start thinking about, and in this example, seeing how we can start to take, so the question at hand, which is estimating the books in the library, and starting to use this information to say something meaningful about the research question here. Okay. People have questions? All right. So what about, we've got a situation, old librarian said that books in the library are 20 years old. What, based on our interval that we've calculated, do we have any opinion about that? What do you think, Katie?
Given the data we have, it's not possible.
Yeah, right? Probably not, right? It looks like our data, based on the data that we've collected, and assuming that we've done a reasonable, new librarian has done a reasonable job of randomly plucking out books, right? It looks like that our old librarian's estimate is probably too low. Right? It looks like the books are probably going to be older than what that estimate is. And how did you come up with that?
It fell outside of the range.
Yeah, right. So lower limit, based on the data we've collected, our lower limit guess for the age of mean average of books in the library is somewhere around 22 and a half years, right? And so 20 years is below that, so it's probably an underestimate, right? Cool. All right. So people seeing how we're trying to take this and not just crank out a confidence interval and writing it down on the page, we're trying to take that interval and make inferences about the task at hand. All right. This is what I'm going to be asking you to do throughout the entire year. So want to think carefully about this stuff. All right. Okay. Going to do another one of these just to make sure that we've got this down. Looking at Flynn effect, people get smarter over time, slowly becoming geniuses. Interested in the Flynn effect. I'd like to know what the current average score would be for an IQ test developed in 1980. Got 120 people, got mean standard deviation of scores. Population mean in 1980 was 100. Okay? So for those of you not familiar, someone tell me what the Flynn effect is.
People do better in IQ tests as time goes on.
Yeah, right. So if we take a test that was developed in the 70s, and Norm said that the average score was 100, if we give it to people now, people are going to score higher on that, right? And this is just something that happens. It's kind of a controversial thing. We don't know why it happens, but it's important why we keep norming scores, because people tend to drift upwards, right? And so we've got someone who's interested in this. And so what we've done is we've taken a test developed in the year of our Lord 1980, like when I was born. Big year for Earth. And so what we do is we take that test from 1980 and we give it to 100 people today, right? And we want to see, do we have evidence for the Flynn effect? Okay, so we've got sample 120. Mean is 107, and our standard deviation of scores is 12. Okay. So what do we need to do first? Standard error, right? Standard error is going to be 12, right, over the square root of 120. Just square the bottom, or take the square root of the bottom here. Should give us standard error of 1.095. You follow me up to this point? Okay. And so we want to take our mean plus or minus, what's our level of confidence here? 2.58, right? I told you I'd try to be tricky. 2.58, and why is it 2.58? Because we got 99% confidence interval, right? Multiply this by 1.095, giving us an estimate of 4.2. Okay. So Sam, within the context of this research question, okay, give me an interpretation, a practical interpretation of that confidence interval.
We can expect that the IQ score for let's see. For the current year, we can expect that the IQ score for the current year will plausibly fall within the range of 104.2 and 109.8.
Yeah, no, that's perfect. That's excellent. That's all right. Right. So again, this is where, and again, if you remember, like me making a big deal over identifying populations, and we're going to continue on with some of that stuff today, right? But the idea is, who's the population that we're pulling from? Presumably people in the world today, right? And so identifying this as, so we would say, plausible bounds for the score on this IQ test from 1980 in the current population, ranging somewhere from 104.2 to 109.8, right? So somewhere between 104 110 points, right? We could talk about this in terms of the lower bound, based on these data, the lower bound limit for our guess of the population, current population score on this 1980 test being about 104, with an upper bound limit of 110, right? We could talk about this in terms of margin of error, right? A lot of different ways we could go through and start talking about this. So this is our confidence bound, but what's our point estimate? Angela, what's our best guess? 107, right? Like if you have to pin us down, we can say, well, I think the population average is 107, but this is my level of precision, right? Again, we're doing a pretty good job because we've got a pretty large sample. Our confidence bound is fairly narrow, okay? And so based on what we described about the Flynn effect, is this something that we would think is in support or not in support of this being a thing? What do you think, Katie?
It would be support,
It would be support, and why is that?
because 100 is not included in
Yeah.
our confidence bound for the current population, so it's not a plausible value.
Yeah, right. So 100 is not a likely value. In 1980, this test was specifically normed so that the population mean was 100, right? But if we give people today this same test, the average score looks like it's somewhere between here and here, but 100 isn't in there, right? Suggesting that we've drifted up and providing support for our hypothesized Flynn effect. Okay. People have questions about this. People are starting to get a sense for what we're looking for with interpretation of these intervals. Calculating them is easy. Interpreting them is a little bit more tricky because it's going to force you to think about what's my population, what does this mean, what's the research question, things along those lines. Okay. Questions about any of this stuff? All right. All right. So, thinking about interpreting our confidence intervals. So, age of our books. Here's our scale in years. Here's our point estimate. Here's our confidence interval, right? The thing to remember, though, and Cumming and Finch talk about this, is that this isn't a square distribution of probabilities, right? We're still working with a semi-normal curve in terms of the likelihood of values within this interval. So again, our best guess, our best estimate is the mean that we've calculated, right? Because our mean is always the best unbiased guess of the population value, right? But we've got some imprecision, and we've created this interval estimate to capture some of that stuff. And so we've got a lower bound of what we're going to call probable, an upper bound of what we're going to call probable. This is directly related to the level of precision that we've selected, whether or not we've got a 95%, 99% confidence interval. But just like our z-score is anything else, technically the likelihood of a value corresponding to the actual population mean starts to get lower and lower as we start to get out towards those limits, right? These limits are kind of arbitrary, right? We could make whatever we want to be, and so the idea of plausible is again got some buzz to it. But is a value of 23 as good of a guess as whatever our actual population mean was? No, right? And as we actually get out towards the end, these boundary values start to get kind of implausible, right? But again, remember that these are kind of arbitrary, and we never want to be working with absolute thresholds, right? So if this is, so our lower bound on this is 22.5 and it's 22.4, and we're like, oh, they're actually not all that different in terms of values. So wanting to think about these things, same thing as the IQ score, right? Just because a value is in the confidence interval doesn't mean that that's as equally good a guess as whatever our mean is. All right. In this case here, we'll work through starting to calculate a confidence intervals on a couple of different samples here. What we've done, I think we're giving rat supplements here, I think. So we've got a sample of 10 rats that we're giving a supplement, and 7 other rats with a separate diet with none of this supplement, right? And then what we do is we give the rats a memory test, that IQ test we were just talking about, in both samples to see whether or not we're seeing an impact of this supplement on on the tests of rats, right? And so what we're interested in here is estimating actual difference in scores between these two populations. So what we're going to do is we've got n equals, oops, 10 for a control, right? In our experiment, n equals 7. Our mean on our test is 25, and our variance is 61. Here, our mean is 33. Our variance is 6.5. Okay. And so, if we take a look at this and we say, is this supplement good for rats? Well, we can say, well, this mean is higher than this mean, right? And so I'm going to conclude that this supplement is good for rat cognition. You want smart rats. Why should I be careful about that interpretation? Need more information. Why, Docs?
Because we don't know if that is.
Right, we don't have a level of precision, right? And remember, as you so cogently pointed out, what's a big impact on our standard error? Yeah, and we've got pretty small participants, right? And so what should we expect in samples of these size? What should we expect from our standard error? Be quite large, right? And so, yeah, these are different, but I don't have a good sense for how are these comparable, are they not comparable, right? And so what we can do is we can start to, or we can go through and calculate our interval estimates around these and start to make inferences from there. So our standard error for our control is going to be 61 over 25, and then we're working with variance, so we'll square that whole thing. Standard error for our experiment is going to be 36.5 over, whoops, 10. Yep, sorry. This one's our control.
36, for control's 36.
Do I get these backwards?
Yeah, no. The results are presented. Unless
No, I probably got this screwed up.
no, then sample are mean of 33,
Oh, do I just,
36. They're just presented backward, like,
You just said control, so she was saying.
oh.
well,
Control issues.
it's still 30.
Yeah.
10 is associated with 36.
Okay.
I think, unless I'm reading it
No,
wrong.
no, I think I've got this screwed up.
Hold on. No, 10 is associated. No, with 36, yeah.
10 is this one,
Yes, and that is the control,
and this is control,
and that's
and that's experiment.
yeah.
Okay. So,
No, it's the
No.
other way around.
Hold up. Experimental 10, control sample.
Yeah. Normal diet, containing, like, okay, sorry.
okay. So we've got our experimental has how many people? How many rats? 7 or 10? 10. And our control? 7. Okay.
I'm sorry.
So did I have it screwed up?
I think the experimental and the control was mixed up, the numbers were weird.
Yeah.
That's why it was confusing.
Okay.
Yeah.
But you were like good with your numbers.
Candace, can you shoot me an email and tell me to make sure my damn examples are correct? Okay, so we've got normal diet, or normal diet containing lectin is 10, is our experimental. No diet is 7. Okay. I think we got it, okay? So we got 61, 10, 35, 7, square root here, square root here, resulting in our, okay. We're correct here, all right. People follow me in terms of we're on the same page in terms of standard errors? Okay. And then if we go through and calculate our interval estimates, we're getting,
What do you have written down for the standard error for
2.8, no, 2. Yeah, it's 2.283, 2.28, there we go. All right. People square on calculation of our intervals, we got it put together. Okay, so calculate our point estimate, calculate our 95% confidence intervals. Someone tell me, Stephanie, tell me what's going on within this set.
There's overlap in the confidence
We got some overlap, right?
interval, which means that there's a possibility that the means might be the same for both samples.
Okay, right. So we've got some overlap. But if we're going through, and that's right, and we're going to talk about how some of this works out, right? But if we take a look, so our experimental group, so we've got this supplement that's supposed to improve cognition. So we give some rats this supplement, right? And we're given our interval here, right? Where does the just group of regular rats that didn't get anything at all, where does their mean value fall? So if this is our interval for the population of rats receiving this supplement, right? This is our upper and lower bound estimate for their score on this test. Right? How does that relate to the point estimate for the rats that we didn't give this thing to? Okay, so it's outside the problem. But in what direction? Above. What do we make of this?
There's too many factors.
Which one is better?
Control.
Yeah, right? Is this a problem?
Well, it's showing us something.
It's showing us
Showing us
something.
what we.
Okay, good. And so this is one of these things you want to go through. This is another trap that you can fall into. You just start calculating stuff and be like, yep, they're different, right? Without thinking about what actually is going on. So we say, oh, we've got this thing, and it should improve memory. So we give some rats the supplement that should improve memory, and we give other rats without it, and then we go through and test them. It actually looks like the rats that we gave supplement to improve their cognition are actually performing worse than the ones we didn't do anything to, right? And so wanting to go through and see, so with our confidence bounds, we can say 33 isn't a reasonable estimate for the average score based on population estimates we've made for rats getting this supplement. Same thing, our upper and lower bound for plausible values for rat performance just normally doesn't contain the mean value that we found for individuals or rats that we've given the supplement to, right? And so at this point in our skill set, we're a little ambiguous in terms of how this relates to everything, right? Because these confidence intervals do overlap to some extent, right? But our point estimates for the respective samples are kind of falling outside of these bounds. But what's nice about this, and particularly for a treatment style study, right? We say, okay, we're going to give these rats this thing that should make them smarter. And then we go through and we say, all right, this is our point estimate for how smart they are. but based on the way we've gone about this, how precise are we? What are the bounds for the level at which they may be performing is what we get here, right? And because we have another sample that we collected as a control, we can start to do some comparison and sort of start to make some inferences about how this stuff pans out. Okay. That was a little confusing, mostly because I had my numbers swapped around or something like that. But people get the idea for how we might start to use these intervals to start making comparisons across groups. Okay. Last thing we'll go through, oh yeah.
Sorry, one more quick question.
Yeah.
Can you go over how we would talk about it in terms of margin of error? Because I know that was one of the possible like explanations of confidence intervals.
Right.
So if I was to explain it less on like these bounds here, but more on the margin of errors or
So you just give me segues into the next slide. High five, nice work. Okay. Alex is a plant. I'm back here. Ask me this question right when I was doing this. Okay. So margin of error stuff, right? This is where, right? See, no, I told you did a good job. Cumming and Finch talk about going through, and this is a a lot of what happens when you're going through and looking at other people's research is you find that they didn't do the things that you wish they would have done. And so what's nice about knowing about numbers is you can go through and kind of reverse engineer and figure out what you need to know based on stuff that they've given you, hopefully, right? And so Cumming and Finch provide some guidelines for comparing different confidence intervals, right? And they're talking about inference by eye and looking at graphical representations, but we can do the same thing just if we've been given just regular old confidence intervals. What we want to do, so this is a graph of the data that we just calculated, right? So we've got a bar graph showing our rats that got the supplement, rats that didn't get the supplement, right? And we see that our confidence bars here, our point estimate falls outside our confidence bound here, point estimate falls outside our confidence bound here, but we do have some overlap in these confidence intervals, right? So the question is whether or not we can start to infer whether or not these two means are reliably different using just the confidence intervals, right? And Cumming and Finch say that if there's no overlap in your confidence intervals, then you know that there's that those things are going to be statistically reliably different, right? But even if there are some overlap, we still might have good evidence for possible reliable difference between these means, right? And so what they are recommending is looking at the margin of error and determining whether or not, if there's no more than about 50% overlap in the margin of error, we would expect our test of these two intervals to be somewhere around p less than 0.05. Okay, and so for the margin of error, so as we calculated, we sort of did a shortcut here, right? So for each one of these, we're going to have, this is going to be 25 plus or minus 1.96 times 2.47. Rajiv, again, I'm sorry because you can't see any of this. And this is going to be 33 plus or minus 1.96 times 2.283. Okay. Where do we get our margin of error? What's that?
What comes after the plus?
Yeah, okay. So this is our margin of error. Okay. This is what we're calculating is the plus or minus on our point estimate, right? And so our margin of error for our experimental group, 4.841, and margin of error for control. 475. Right? Maybe we'll see where you got that margin of error. Okay. And so, Cumming and Fitch recommend is if you take, assuming that yours have samples of at least 10, which we don't, and no more of a difference in your margin of error than a factor of 2. So basically, if you got reasonable samples and your margin of errors aren't hugely discrepant, then you just recommend taking the average of that, right? So we take the average of these two, we get an average of about 4.658, right? So that's looking at our average margin of error. And then what we want to do is we want to calculate the amount of overlap. And this is where things can get a little bit tricky. But what we want to do is make sure we get the values that are corresponding to our overlap. So we're going to take for our larger point estimate, the lower bound for that, and for our shorter mean, the upper bound. Okay. So our overlap in this case is going to be 29.84, right? The lower bound, the upper bound of our lower limit. Yeah, the upper bound of our lower limit minus 28.53. The lower bound of our higher mean gives us an overlap of 1.31. Okay. And then what we want to do is just see about how much overlap, sort of magical numbers, looking at about 0.5, right? And so we want to see, well, this is our margin of error. So we've got 1.31 over 4.658. It's about 0.281, right? And so what would we, based on Cumming and Finch's guidelines, what would we conclude about the likely difference in these two means? And we've got less than 10 people in one, but again, it's probably pretty close. Would we, based on Cumming and Finch's eyeballing things, are we likely to conclude that there's a reliable difference between these two means? Yeah, Sam, why?
Well, based on high volume, it's not, based on that, it's not good.
Yeah.
I don't know about interpret from that number.
Better interpreted? Well, it's just, this is saying that our confidence bounds, there's about 28% overlap in our margin of errors. Okay. So, and what we want is looking in and say, so if we've got, say something that looks we've got about 50% overlap here, right? There's a lot of overlap, and so we would probably, in this case, say that we probably don't have sufficient evidence to conclude that these two things are likely different, right? But if we shorten these up, right? It's a crappy drawing, but or just use what we've got. In this example, right, we've got some overlap, but it's not a lot, right? And so this is what will happen sometimes. Is sometimes you'll read a paper where they didn't actually perform whether or not these two things are different, right? They didn't do a statistics test, an inferential test to see if these two things are different, right? They just said, oh, these are a couple things. But maybe for your study, it's important to know whether or not there's a reliable difference between these two things. If people have provided means and standard deviations and sample sizes, you can go through and just test whether or not these are different on your own, right? Company and pitch talk about looking at this and kind of eyeballing things, right? But this is a nice way to start to reverse engineer some things using your confidence intervals and looking at percentage of overlap to make a determination on whether or not things are likely different. Okay. This can get a little bit tricky, making sure you're sort of like, which ones do I subtract from which ones? The good thing is if you do it wrong, it looks wrong. So you'll probably be able to figure out that you've made an error somewhere in this. Questions? Okay, work on this. As you go through, work on it, help each other out. If you have problems, come and talk with me. Again, asking you to do this on one of the questions in the assignment. Okay. All right. Formatting and reporting your confidence intervals, lower, upper, things like that. Here's what something might look like if you were reporting it within the context of an assignment or something along those lines. So, general information on that. All right, cool. Let's take a break. When you come back, we'll jump into our next lecture and then be off to the races on standard errors. Exciting stuff. All right, cool. Take a quick break. Let me know if you have questions on stuff. So, want to just make sure everybody's got a reasonable handle on confidence intervals. Okay. All right. Going to jump into distribution of sample means, some hypothesis testing stuff today. Up to this point, most of what we've worked on is looking at, with our z-scores and things, and with this problem set 3, what you're doing, identifying the location of a score within a distribution, right? So you've got your distribution of scores within a sample or in a population, and you're going through and saying, all right, here's where this score is, this is where the z-score is, and it's likely, this is the probability of obtaining a score at this level or higher, assuming a normal distribution, right? But when we're starting to get into our actual research questions, we're rarely, if ever, interested in a single score, right? Like Morgan, nothing against you, I could care less what your score is in the sense of larger population. That's not relevant to my research interests, right? But what we often are interested, right, is in making inference based on where our mean is from our sample of scores, right? So I go through and I collect a sample of height from individuals at the University of Wyoming. I want to know where this mean falls, my sample mean falls relative to other means that I could grab within a distribution, okay? So just like we've looked at representativeness probability of specific values within a distribution, right? So I can say, here's the distribution, here's the mean standard deviation. Is this score a likely score, or is this score a representative score within a distribution? What we can do is we can start to extend these same types of concepts to look at the representative probability of obtaining a specific sample mean, assuming all other possible sample means, okay? If I were to do this again and again and again and again and again, right? Is this sample mean that I've found, is this a likely sample mean or a probable sample mean? Or is this something that starts to fall way outside the bounds of what I would expect given multiple replications? Okay? And so what we need to do to start working with this, and this is the foundation of all of our inferential statistics, working with the distribution of a sample statistic. We're going to be working on means now, but this is the same idea corresponds to any type of coefficient we're looking at running a test on. But within the context of means, because that's what we've been working with, we're talking about distribution of sample means. Distribution of sample means is our distribution of means from all possible random samples with replacement of a particular size that could be drawn from the population. Okay? Again, before what we were talking about is values in a distribution, being individual scores. Within the distribution of sample means, the values of individual scores are means of a sample. Okay? So if we're thinking about in practice, right, if I want to know the average height of people in the US, right, of sample 100, there's almost, not literally, but functionally, an infinite number of samples that could be drawn with replacement from the US population, right? And so it's impossible to calculate, account for all of these possibilities within an applied sampling strategy. But what we can do is people smarter than me have gone through and worked out the mathematics behind this, and so we can start to make inferences based on parameters of our data and just the way things work out in nature. So as a demonstration here, okay, we've got population of 4 scores. These 4 scores, 2, 4, 6, and 8, these are all the values in the universe in this population, right? So it's just 4 people, right, or 4 units, whatever. Okay, so this is our graph of the population. This is our distribution of population scores. Okay, here is our mean of the population is 5, right? Katie, how would you describe the shape of this distribution? Mm-hmm. Just a square distribution, right? We've got 4 scores. Everybody has a different score. It's just kind of, it's symmetrical, right? But it's just a flat distribution. We call this a square distribution. Okay. So, people comfortable with our population of 4? All right. What we can do from this population, and again, we've made it simple for obvious reasons, is we can then start to create a sampling distribution from this population. And to create a sampling distribution, what we're going to do is we're going to create a sampling distribution of means given a sample size of 2. Okay? So what we're going to do is we're going to say, or we're going to go through and list out all possible samples of 2 that could be drawn with replacement from this population. And because we've only got 4 scores, we're limited to 16 unique samples that can be drawn with from a sample size of 2. Okay, so we've got first sample 1. First score was 2. Put the person who had a value of 2 back. Reached in, pulled them out again. We got score of 2 and 2 here. Okay, same thing. Second sample, we get 2, 4, 2, 6, so on and so forth. And so you'll see at several places, because we're sampling with replacement, we've got the same score both times, right? But from a mathematical standpoint, this is an important factor in calculating your distribution of sample means. Okay, people see what we've done here? So this is literally all possible samples of size 2 that could be drawn from this population. We've listed them out, right? And then what we're going to do is we're going to calculate the mean of all possible samples of 2. If we go through and calculate the mean, here's the mean of all possible samples of 2. What we're going to do then is we can go through and graph these means out. These means produce a distribution for this population of 4 scores. This is our distribution of all possible sample means for n equal 2. Angeline, how does the distribution of sample means compare to our actual population distribution?
This is a normal distribution.
Yeah, it's a normal distribution, right? Our population, our distribution of sample means starts to become very normal very quickly and looks a lot different than, or oftentimes looks a lot different than our population of actual scores, okay? And so that the mean of the sample means is going to be the same as the population mean, okay? This is super, super important because we can't ever estimate the we can't ever measure the population mean exactly, right? But what we know is that the mean of the distribution of sample means is equal to the population mean. So our population mean here is 5. Raji, what's the mean of our distribution of sample means?
5.
5. How do you know that?
It's a normal distribution.
Yeah, I mean, it's a perfectly symmetrical distribution, and that's the middle score, right? But if you went through and were to add all these up and calculate it, you would get the mean of the sample means is going to be 5, the same as the population mean. Okay? Distribution of sample means generally form a normal distribution, and what we can do is we can start to use our distribution of sample means to start answering questions about the likelihood or probability of randomly selecting a sample of a given size from this population. Okay? So for this here, Stephanie, if we say what's the probability of selecting a sample having a mean of greater than 7 in our distribution of sample means?
I would look at the Z table.
You don't even need to look at the Z table.
Oh.
If you just look at, it's within the context of this example, if you're looking at this, what's the probability of selecting randomly drawing a sample of 2 having a mean greater than 7? What's that?
I'm sorry, I'm guessing, but because I don't know like the percentiles yet.
Okay.
The normal distribution, but I would
Okay,
say.
so do we need a Z-table normal distribution to calculate this? No. Wait, Alex, you're shaking your head. Can you help us out? What's the probability of randomly selecting a random sample of 2 with replacement that has a score of 7 or greater than 7? You can use fractions if that's easier. 116. Okay, Morgan, how did you get that?
You just added up the cubes.
All right. Okay. Yeah. No, and so in applied setting, right? Like so, and so this is how. So we've got this is our distribution of sample means, right? It's a very simple distribution of sample means. How many samples that we've got, or how many sample means are greater than 7? Just 1. How many possible samples can we get of sample size 2 with 4 scores? 16, right? So it's just one of 16, right? But this is important to think about. This is how our statistics work, right? This is the analog of how, because those values in the Z table or the T table, they're not just random numbers, right, that we've got. They actual correspond to actual probabilities, right? So in this very simple example, the population of 4 scores, if we randomly are selecting with replacement samples of 2, this is all the possible samples. These are the total possible unique samples that we could get, right? And then what we can do is we can start to make a determination on the likelihood of randomly selecting a sample having a certain characteristic. Is it likely that we would randomly select a sample of 2 having a mean greater than 7? Why not? Anyone?
Because you have like a 6%, 60%.
Yeah.
It's like on the tail.
It is very unlikely, right? And so if you were to select a sample with a mean greater than 7, that would be kind of a rare event, right? It wouldn't happen very often. We wouldn't expect that to happen very regularly, right? And so this is how we start using, again, taking the same principles we've worked through up to this point, to take this idea of, instead of finding the probability of selecting a given score from a distribution of scores, whether it be a sample or a population, going through using distribution of sample means to start to calculate the probability of drawing a sample of a certain characteristic, given all possible samples that could be drawn of that size. Okay. And so this relates directly to our central limit theorem. For our actual populations, we're using mathematical theory to start to make inferences about characteristics of a population. Central limit theorem states that for any population with a mean of mu and a standard deviation sigma, the distribution of sample means for a sample size n have a mean equal to population mean and a standard deviation of the population standard deviation divided by the square root of n, and we'll approach a normal distribution as our sample size starts to approach infinity. Okay? It gets normal way before we hit infinity, but mathematically, this is the principle, this is the proof that serves as the foundation for almost all of our inferential statistics. So what this means and what this looks like, okay? We have here a hypothetical distribution of sample means for random samples of adult height with a sample size of 100, okay? What this means, and let's say, again, we're using the U.S. population as, or people in the U.S. as our population, right? If we went through and randomly, in a true random sample, went through randomly selected samples of 100 people with replacement, recorded their mean height, and then did that for all possible random samples of 100 that could be drawn from the U.S. population, this is what our distribution would look like. Okay. So Morgan, within this distribution, what do individual values in this distribution correspond to?
Height.
Height, but what height as in how? Not units, but what type of height? Like, so what do these values actually represent? Height of an individual, height of.
It looks like millions of people.
Okay, right. Are individual scores in this distribution? Are these scores for individual people or scores for samples of people?
Samples.
Samples, right? So this is kind of asking you to take this just a higher step up. Each data point in this distribution is a sample mean, right? Of all possible samples that could be hypothetically drawn with replacement from the population of individuals in the U.S., okay? And so what we see is that our distribution of sample means starts to approach a normal curve under two of the following circumstances. These are very important. I'm going to ask you spontaneously when I see you out on the street this type of stuff, right? Two circumstances. One, population from which a sample is drawn is normal, right? So if I'm studying something, if I'm looking at a phenomenon or that has a normal distribution of scores, let's say levels of shyness, right? Some people are very shy, some people aren't very shy. Personality trait, I'm assuming that occurs on a normal distribution. Distribution of sample means for shyness is going to approach normality, approach a normal distribution very, very quickly because the actual phenomena of interest actually follows a normal distribution, right? So, one, if population from which sample is drawn is normal. Two, if our sample size is about 30 or more, right? So even if we have a really ugly distribution, if I'm looking, someone give me an example of something that probably has a poor distribution or a skewed distribution or something that's really funky.
Substance use?
Substance use, right? So if we were to look at cocaine use, right? I would hope that cocaine use doesn't have a normal distribution in the population, right? So it's probably got a right tail on this, right? But if we're sampling cocaine use in a sample of, say, 50, 100 people in our sample, the distribution of sample means for that distribution is very, very quickly going to start to follow a normal distribution, okay? So our sampling distribution of sample means starts to become normal quickly if one, phenomenon of interest has a normal distribution, or two, we're using reasonably large samples. Okay. Questions about this? All right. So this is shape of our distribution. Central tendency, mean of the distribution of sample means, right? Think about this, the average of all possible sample means of a given size is equal to the population mean. Okay? Talk about here, if we say the population mean of height for individuals in the US is 68 inches. The distribution of the mean of the sample, distribution of sample means, we call this our expected value of the mean. The mean of this distribution is also equal to 68 inches. Mathematically, these things are equivalent. Okay? Our expected value of them refers to the mean of a distribution of sample means equal to the population mean. So what happens is we don't have to actually observe the population mean. Mathematically, the distribution of sample means should approach the population mean, assuming sort of we've got a reasonable sample to work from. Okay. Questions about central tendency? Yeah.
So is this also a reason why things become more normal because we're taking averages of samples?
Exactly, right? So we're taking averages. So if we'll get to this in another demonstration. So even if we have a distribution that's very skewed, right? What's the likely distribution of cocaine use if we're saying use number of times a year, and I just go through and randomly grab up 100 people? Probably it's going to be pretty close to 0, right? But if I go through and I do it again, that next sample is probably pretty close to 0. And I do it again, sample is probably pretty close to 0, right? So my means that I'm getting, even though the distribution in the population is skewed, most of the time I'm going to get something that's not exactly 0, but something above 0. Most of my values are going to start to pile up around there. Sometimes I'm going to get a lot of cocaine users, and it might be a little higher. A lot of times I'm going to get people who don't use at all, and it's going to be lower. But the mean of that distribution of sample means is still going to be normal, even though the actual distribution is not very normal at all. Okay? So you're exactly right, Sam. It's basically because we're working with aggregates that start to filter out some of that skew. Does that help? Okay, cool. All right, other questions about the central tendency of sampling distribution? Okay, finally, measure of variability. Okay, this is your standard error. We just talked about this. Standard error, the mean, is the standard deviation of your distribution of sample means. Calculate this as standard deviation over the square root of your sample size. Okay, so here, population standard deviation is 6 inches. Standard error, the mean in the population for samples of 100 is going to be 6 divided by the square root of 100, 6 divided by 10, 0.6, right? And this 0.6 represents the standard deviation of your distribution of sample means. Okay? So, if you've internalized, and hopefully you have, interpretation of standard deviation is the average distance of any score from the mean, or to the average amount of error expected in any given randomly selected value, or the average distance or the expected difference between two randomly selected scores. All of that translates directly into understanding your standard error. A couple different ways we can think about standard error. Index of how much difference is expected from one sample to the next. Here we've got a pretty big sample, right? At least by psychology standards, right? And so because we've got a pretty big sample, do we expect our average height to jump all around a whole lot from sample to sample? Stephanie?
Can you repeat
I
the question?
said, given a sample of 100, do we expect this? Do we expect our mean values across random replications to jump around a whole lot? No, right? So we might expect, I guess based on this example, on average, we would expect any two randomly selected replications to differ by about a half an inch, right? Because we've got really big samples, really stable samples. We're not expecting them to jump around a whole lot, okay? And in contrast, I went through, I'm working with some data right now, I'm estimating correlation coefficient, but I'm working with like samples of 10, right? If I'm looking at the correlation between X and Y in a sample of 10, how much would should I expect that correlation to jump around just based on random replications? A lot, right? Because it doesn't, if a sample of random, with a sample of 10, it doesn't take much to throw that way off, right? And so I'm going to jump around a whole lot because I'm working with a small sample. With large samples, we're expecting these replications across these estimates across replications to be pretty close here. So think about standard error conceptually, practically, as the amount of difference expecting from one sample to the next. You can also think about it as how well any individual sample that's that we collect estimates the population mean, right? If we're conceptualizing our standard error as to the average distance between any two scores of the average distance from the mean, do we want large standard errors or small standard errors if we're looking to get a reasonable representation of the population parameter? Small standard errors, right? And literally thinking about your standard errors, how well does this estimate the mean, right? If I'm looking at something on a 0 to 100 scale and I've got a standard error of 4, it's not bad, right? If I'm measuring something on a 0 to 10 scale and I've got a standard error of 4, I'm less excited about that, right? And so thinking about your standard errors that you're calculating is how much you're expecting things to jump around and how much error you're expected to be off of your actual intended population parameter. Also thinking about standard errors, the expected difference between sample mean and population mean, right? Here's what I estimated. How far on average would I expect this sample to fall from the population mean? Now for any given sample, do I know that the population mean is no more than 6 inches away? You're shaking your head, Angela. No, why not? You're absolutely right. Why not?
Unless you have the entire population.
Right.
You can't know that.
Exactly, right? Because you know what? Some of these sample means are falling way out here, right? And if you're that far out, hopefully you recognize that you're that far out, right? But these are values that occur within this distribution, right? So we could get a sample of 6'2", right? That's way outside, but it's just a weird sample, right? So on average, I might have, my standard error might be about a half an inch. And even though I've got a huge sample, sometimes just randomly I'm going to get stuff hanging out here, right? So again, recognizing that these interpretations are for considering sort of multiple, all possible replications of that could be conducted. We're expecting us to be around here. We're probably somewhere around here, right? But we can also end up hanging out way on the ends too. Okay, and we'll talk about this more as we get into some different types of tests. Questions about our distribution of sample means or standard error? Okay, memorize this, know this is important stuff. You can't do statistics without, at least parametric statistics, without standard errors. Standard errors are sort of the basis for everything that we do. I want you guys to have a good understanding of this. So, factors influencing standard error. Standard error decreases with population standard deviation and the sample size. The larger the sample size we have, the more likely that it's our sample mean is going to be close to the population mean. It's really hard to get these samples, right? These are infinitely unlikely to have a random sample of 100 people and get an average height of 6'2", right? It's not impossible. This is like winning the lottery. It just doesn't happen, right? If we've got big samples, they tend to fall in here. We have more confidence that they're going to fall in here. If we have small samples, it's really hard to tell. It's easier to get extreme samples that aren't represented error. Again, taking this as a standard deviation divided by the square root of n. we talk about the sampling distribution, or this distribution of sample means starting to become normal as your sample size hits about 30-ish. That's a general rule of thumb. Don't try and claim that your sample of 30 is large and robust to sort of violations and things like that, right? I mean, in certain settings, cell sizes of 30 can be quite large. But again, what we're looking at, is we're mapping out your standard error. All other things being held equal, across the different values of n, we see that somewhere about in the 30th range, that standard error starts to taper off. It'll continue to go down, right? And it'll become asymptotically close to 0. But we get a lot more bang for our buck by adding people with small samples than we do adding people on large samples. So the relative reduction in standard error going from a sample of 10 to 20 is a whole lot more than the relative reduction in your standard error that you get going from 110 to 120. Okay. But continues to go down, and again, your standard error, that's going to be in the denominator of all your test statistics, right? And if the denominator, your test statistic is lower, Alex, what does this do to your test statistic? Right, I spit on you from here.
If the denominator is lower,
The denominator is
output
smaller.
Oh, yeah, the denominator is smaller than the output is higher. So
Right. We get bigger test statistics. It makes it easier to claim statistical significance the smaller our standard errors, and so sample size is the primary thing that drives this down. There are other things, but sample size is the primary driver. Okay. So again, we go through and say distribution of sample means. If we've got sample means of, I guess of different sample sizes, which of these graphs, Rajiv, is indicated, if this is a distribution of sample means, which one of these corresponds to our largest sample and which one corresponds to our smallest sample?
The largest sample would be the black curve, and the smallest one would be the blue, I guess.
Yep. How do you know that?
How the curve is distributed along it's more distributed, means it's more flat, that means it's getting more.
Right. We've got more variability. This is a really small sample, right? It's still normal, right? And the mean of the sample mean, the expected value of the mean across all of these is still 100, right? But as our samples start to get larger and larger, it starts to bring in that variability. The expected difference that we would expect across replications of this these samples start to get smaller and smaller. Things start to get tighter and tighter as we pull in here, and so we can see that here it's pretty easy to get stuff falling way out in the margins if we don't have a very large sample. But as soon as we start getting larger and larger samples, things start to stay pretty tight in with the true population parameter. Okay. Questions about this? People see how this is kind of playing out here? Okay, so tying this all together, at this point in this semester we talked about 3 different distributions. Important to keep these separate into your head. We've got distribution and population scores. Okay. Population, this is all the scores within a hypothetical population. Our distribution and population scores has its own shape, mean, and variability. It's not an estimate, it just is whatever it is, right? And we also have a distribution of sample scores. This is a subset of scores drawn from the population, hopefully to be representative of the sample, but our distribution of any sample that we draw is going to have its own shape, mean, and variability. Then we have a distribution of sample means. This is the distribution of sample means from all possible samples of a specific size that we could draw. Has its own shape, mean, and variability. So if we go through and we take a look, we've got, here's our population mean, right, of IQ scores. This is, and again, if our population, important to identify what's the population that we're talking about. Talking about, say, everybody, US citizens, distribution of IQ within the US population. I can go through, and we've got, in the population, we've got a mean of 100, standard deviation of 15. But I can go through and randomly select a sample of 30 people and sample them and measure IQ. And we've got a very different shaped distribution than what we have in the population, right? We've got a sample of 30, right? This is our large sample. We would expect in this sample, the sampling distribution of IQ for sample size 30, is this gonna, is our sampling distribution gonna approach normality quickly? Yeah, so we're sampling IQ scores at a sample size of 30. Is the sampling distribution gonna approach normality very quickly?
Yes.
Yeah, why is that, Sam?
Because the 30s, it's not arbitrary, but it starts becoming.
Starts to become okay, and what else?
Standard.
What are the thing impacts distribution of sample means? What's that? Yeah, what about the population? Yeah, what about it? It's normal, right? This doesn't look super normal, right?
Right.
This doesn't look super normal, but the population from which it was drawn is normal. So between the sample size that's reasonable and the fact that distribution of actual scores, the phenomenon is normally distributed, even though this doesn't look super normal, the sampling distribution of this is gonna look really normal really fast, right? And so we see we've got the population mean standard deviation. Our sample of 30, it's got a different mean, different standard deviation. Looks similar, right? We've got a decent approximation here, but we're gonna have, we're not gonna be exactly on point. Katie, what do we call it when we have differences between our population mean and our sample mean? Not quite.
Can you repeat that?
Okay, when we have a difference, what do we call a difference between our population parameter and our sample statistic?
Measurement error?
Close, not measurement error.
Measurement bias?
Not measurement. What is it? Sampling error, right? Sampling error. Sampling error is the difference between our population and the parameter and our sample statistic. So this here is our sampling error. Again, doesn't mean that our sample isn't any good or that our sample is biased or anything like that. It's just something that happens, right? So we've got our sampling error here, but what we've got then also within for a sample size of 30, right? For all possible samples of size 30 that could be drawn from the population of the US, the distribution of sample means very quickly starts to become normal, right? And our sampling distribution of sampling means here has its own mean, but that mean is equal to what? Population mean, and it's got its own standard deviation. And what do we call the standard deviation of the distribution of sample means? Standard error, right? And it's just the measure of standard deviation, measure of variability within the distribution of sample means. And so these three things all together, wanted to keep them separate, but if you've got this down, you've got a good start on having a strong understanding of our statistical procedures, what's going on, and the sorts of things, the types of things that start to throw this way out of bounds. Yeah.
Is there a link between sampling error and standard error?
Yeah, yeah. What would be the applied what would be the applied consequences of sampling error for standard error? Okay. Calculate standard error. as, right? What's sampling error going to do if it's systematic? It's going to increase your standard deviation, right? Right? And if we increase our standard deviation, what does that do to our standard error? Increases our standard error, right? So if we're using imprecise measurements, right? If we're not using good instruments, if we're not using good procedures, right? This is going to systematically, all things being equal, it's going to increase our sampling error, right? If we increase our sampling error, it's going to increase our standard deviation of any given sample, right? Our things are going to jump around a whole lot. If, again, it's a silly example, but I think it's, so if I'm measuring people's mass, right? I could get a scale and I could measure things on a scale, and people are going to weigh different things, but if whatever they weigh, I'm going to be pretty close on what they weigh, right? Or I can have people come in, and I can have you just come up and I can just pick you up and make a guess on how much you weigh, right? So then not only are we've got error differences in how much people weigh, we've got variability in me just picking people up and saying, I 130 pounds, and putting you down and letting you walk off, right? So we've got an imprecise measure that's adding into variability, which is going to increase systematically my standard deviation of my measurement. I'm just going to have more error in the equation. So the more error we get in the equation, the larger it's going to turn into our standard error. This is where the methods piece starts to work in and making sure we're using good methods, because that's just going to help us when we're running our statistics.
Okay, so if there's a discrepancy that from the sample mean from the population, that means if I get a lot of those, they're gonna like have a greater variability in the sample distribution.
Well, so we're using, in terms of calculating our standard error, we're using the best estimate we have for standard deviation, and that's the standard deviation we pull from our sample, right? But if we're using precise measurements, right, our standard deviation is going to be smaller than if we're using imprecise estimates. Now, all things being equal, we're still, the distribution of our sample mean is still going to equal the population mean, even if we've got crappy measures. It's just our standard error, our distribution is going to be a lot wider than it would be if we had good measures, right? And we're always looking for small standard errors, because that helps in terms of the precision of our estimates. Okay? So sampling error is something that's going to happen all the time. We just want to reduce the degree of systematic sampling error that we have, because that's going to help out with this other stuff. Cool. All right. I'm out of batteries here. Okay, so why this is all worth the time of working through this. Function of the distribution of sample means what we're trying to do is detect the probability of selecting a sample having a certain type of characteristics. Okay. What we want to do with our hypothesis test is determine the probability of randomly selecting a mean with a sample with a mean X or greater, or something along those lines, right? And so what we can do is we can start to use our z-scores that we use to calculate the probability of individual scores, take this, map this on, and start using this to calculate the probability of getting a sample having a certain mean of this level or higher, okay? Same methods to locate probability with specific scores. We're just going to start locating probability associated with obtaining specific samples. Z-score formula is almost identical to what we've been doing before, except here, instead of having an X value for an individual score, we're going to take our sample mean minus some hypothesized value that we would expect for the population, and divide that by the standard error. Formula is the same, we're just replacing a couple different pieces with a couple other pieces and doing conceptually the exact same thing. So for example, if we wanted to know, say, SAT scores from a normal distribution with mean of 500, standard deviation of 100, what's the probability of selecting a random sample of 10 students with an SAT score less than 440? Using our z-scores, we can go through and calculate this. We could also calculate the likelihood of selecting a random sample of 75 students with a mean SAT score less than 440, right? Which probability, which is more likely? Scenario 1 or scenario 2? What do you think, Katie?
What are you wanting to?
Okay, so we got two situations. We got the same question, except here we're probability of selecting a random sample of 10 students with a score of 440 or less. Here, a sample randomly selecting a sample of 75 students with a score of 440 or less. Which one of these scenarios is more likely?
Would it be the first one because there's a smaller sample?
Absolutely right. Neither one of these is probably super likely, right? Because we're looking at over half standard deviation below the mean here, right? But it's going to be a lot harder to randomly, accidentally get a sample, a randomly selected sample of individuals falling below a score of 440 if we've got a larger sample than a smaller sample, right? And why is that? What do we expect from our larger samples? They're more representative, right? And so, and particularly if we then say 100, 200, right? That starts to get very difficult. Very rare to get a sample, randomly select a sample at that level, okay? We could also range of mean values for sample of N25 could be expected from the middle 80% of the distribution. Doing all the same things that you're doing in your current assignment, except now what we're doing is we're talking about the probability of selecting a sample with these characteristics, assuming something that's known about the distribution of the population. Okay. So when we start to interpret patterns in our data, okay, so let's say that we do go and we find something that's atypical and unlikely. Two possible explanations. One, what we're seeing is some systematic factor that's associated with something that's actually going on in the universe, right? This is a true thing, right? We see, on average, that average height of women tend to be lower than the average height of men, right? This is a thing because biologically, women tend to be shorter than men, right? That's just something that is, right? Or we might find that the pattern is a result of just chance fluctuations that just happens to be for one reason or another, right? We find that in our sample, we find that women more often have blue eyes than men, right? Is that a thing, or is that just something that happened to happen in this sample, right? It's tough to know which one of these is which by just eyeballing the data. Okay? And so what we do, we've got a set of tools referred to as null hypothesis significant testing. And our null hypothesis testing provides us with a set of procedures that we use, for better or for worse, to start to structure our inferences about phenomena that we observe out there in the universe. Okay? Ultimately, the goal of our hypothesis test is to start to tease apart what's real systematic effects that are likely to replicate, and what's stuff that is maybe just due to random fluctuations. Right? I collect people and I see that it has an average score of 57. does that likely reflect true differences in the populations from which, respective populations from which these were drawn? Or is this just static noise that is what we would expect based on random draws from the same distribution of sample means? This is what we're trying to differentiate with our null hypothesis testing. So for our hypothesis test, our statistical procedure, using sample data to try and make some inference about a population. For example, what we do, if we assume that some population has a mean of whatever that mean is, right? What we want to do is determine the probability of drawing a sample of that from that population that has a mean of some value or higher or lower, right? And if we find that the probability of randomly selecting a sample with these characteristics is exceedingly high or low, what we do is we typically will start to conclude that it's unlikely that the sample that, or the population that the sample was drawn from actually is consistent with whatever the reference parameter is. Okay? So to try and solidify this, let's say we know that rats have an average weight of 400 grams because we work with rats and they're bred and they're pretty much clones of one another. They're all pretty consistent, right? And so we have rats with a known population mean, right? And so what we do is we go through and we take a sample of rats and we give them some medication, some unknown treatment that's supposed to do something with their weight, okay? We don't know what the population of medicated rats is. We don't know what their average weight is, right? That's a hypothetical we don't know, right? But what we can do is we can take this treated sample and we can measure, use them as a representation of this hypothetical population of treated rats, and we can weigh them after they've received whatever treatment that they have, right? What we can then do is say, all right, here's the average weight of rats that have been treated with X. These rats that have been treated with X are representative of the larger, the hypothetical population of all rats that could be treated with X. And we're treating this, the average mass of these rats as representative of the population, right? Now, if we go through and what we want to do is we say, and let's say that our observed mass here is 450 grams, right? What we want to do is we say, all right, well, we've got a population of rats that we know has a mass of 400 grams. And assuming that this treatment doesn't do anything, what would we expect the population of treated rats, their mass to be? 400. It'd be the same, right? But what we have is we have a set of rats that doesn't have a mean mass of 400. They have a mean mass of 450, right? What we're trying to do with our inferential statistic is say, is this enough? Is our observed data discrepant enough that we would say that it is unlikely if the actual mean of the medicated rats was 400, if this treatment doesn't do anything, would we be likely to find a sample of rats with an average mass of 450? Or is this something that would be very unlikely, which would lead us to maybe conclude that probably the population mass for rats that have been treated is probably something different than what our known population parameter is. Right? This is our null value, and so this is how we go through and we start to set up these z-tests to start running our inferential statistics. Okay. People kind of have a headspace on what we're trying to do with this. Okay, so we've got an example. So researchers believe that supplements may reduce age-related cognitive decline. We've got a sample of 25 adults aged 65 or older that take supplements for a period of 6 months. Participants are given a neurological test to assess cognitive functioning. Scores for this test are known to be normal in the population, with adults 65 or older scoring an average of 80 with a standard deviation of 20. So what we've done, what we want to know is whether or not taking supplements is actually having an impact on this sample of older adults. And so we know that that the population of older adults, 65 or over, this is where they score on this measure. So what we can do is we can have, pending appropriate IRB approval, right? We can go through and we can have this sample of older adults taking this medication, take a look, have them take the test, and then see where they're at, right? And if we find that this people in our sample who now represent a different population, right? These are population of adults who take supplements. Is it likely that we would find them to have this level of characteristics in that they deviate largely from the known population, or are they somewhere in the vicinity? And if we do see differences, we can probably just chalk that up to just random fluctuations that we would normally expect in our distribution sample units. So what we're going to do for our hypothesis test, first thing we're going to do, we're going to state our hypotheses. What we're doing is we're, in a best case scenario, predicting characteristics of a sample to be collected. We're saying, assuming that these supplements don't do anything, what do we expect the population mean of cognitive achievement for our older adults to be for the population of adults taking these supplements? What do you think, Sam?
Could you repeat the
Yeah, that was not a good question. So we've got our population of adults, right? But now we've got these adults that we've sampled that are a part of the new population. These are population of older adults who take supplements, right? Assuming that the supplements don't have anything to do with anything, what would we expect the average score of this cognitive test to be in the population of older adults who are taking supplements?
stay the same?
Yeah, right, we would expect, assuming that it doesn't do anything. I mean, technically they're a different population because they're a population that's doing something, they're a group of people who are doing something that this group of people aren't. So they're a separate population, but assuming that whatever makes them different actually doesn't impact cognition, we would expect them to still score 80 and have a standard deviation of 20, right? So what we're going to do is we're going to state this again before we go through and collect the data. We're going to set the probability for determining what we're going to call a reliable effect, calculate our sample data, include our relevant statistics, and then we're going to go through draw conclusions about behavior based on our results. So, step one, I'm going to state our hypotheses here. As a recap, and this probably isn't new business, but recognizing that our hypotheses actually involve a couple of competing hypotheses. Our null hypothesis almost always is going to be that there's a zero relation between the IV, the DV within the population, right? This can take a lot of different forms. We can say that group A and group B are not going to be different in height. We can say that grouping variable is unrelated to outcome variable. We're saying that treatment or our manipulation has no effect on outcome, right? Basically, our null hypothesis is saying there's nothing happening, right? Even though sample or older adults who take supplements are their own specific population, we're assuming that supplements don't do anything in terms of their cognitive ability, and so their parameters are going to be the exact same as what we see in the larger population that don't take supplements. Okay. So this is our null hypothesis. Our alternative hypothesis is that there is a relation between our IV and our DV and our population. That treatment does have a reliable impact on outcome. There is a difference between these two groups, right? This is going to be our alternate hypotheses. Our null hypotheses tests are only set up to test our null hypothesis. Again, probably not new information if you reach back into undergrad statistics. This is something that gets hammered home and then we immediately ignore it when we're out there doing our own stuff. But our tests, this is just kind of there for show, right? This is just sort of a statement of, well, this is the opposite of the null hypothesis, right? But based on the evidence that we conduct in our, that we gather in our inferential tests, we either reject our null hypotheses or fail to reject the null hypotheses, okay? We don't confirm the alternate hypotheses. We actually don't confirm anything. We actually don't confirm the null hypothesis either. All we're doing is we're rejecting or fail to reject our null hypotheses based on the data that we've collected. Null hypothesis is the only concern in terms of our interpretation. Okay? For our supplement example, right? Our null hypothesis means put this in symbols, and then we can write it out in terms of actual words. We say our null hypothesis here is our supplement mean cognitive performance, and our supplement example is 80. Morgan, where did we get that?
I think that's the
Right, that's our reference point, right? We're assuming that these supplements have no impact, right? And so we've just set our null value to what we would expect from the larger population. We're saying the population of older individuals using herbal supplements is equal to 80, okay? Our alternate hypotheses, supplements not equal to 80, right? We're just saying we're not making a prediction on which direction it's gonna go. We're just saying it's just not 80, right? Population of older adults using herbal supplements not equal to 80 on whatever test it is that we're running. Okay. Notice this. Circle this, highlight this. Did I say sample in any of this stuff? See the word sample in any of that? No? Why not?
Because they're not making the inferences about the sample.
Yeah, I don't need to make inferences of a sample. You just look at the damn sample and tell you what the value is, right? I got a mean of 78. 78 is not 80. I don't need an inferential test to do that, right? Because we're not interested in the sample. We're interested in the population. We're trying to make inferences about the population, right? The sample, who cares about the sample, right? Our hypotheses are always geared towards the population, right? And so as you all are working through this, I want you to be focusing on this, and this is where things start to become difficult because you're making statements about the population, which is going to force you to recognize who the population is, which is going to make an impact, force you to think about who this generalizes to, who it doesn't generalize to, these types of things. This is a good exercise. So in your hypothesis statements, if you start saying the word sample, you're going to get points taken off, or at least sort of highlights and red pen and things like that, because we're never talking about the sample, right? The hypothesis is never that the sample mean is 0, right? Or that the hypothesis is never that there's no difference in the samples, right? Our hypothesis is always trained to the population, and I want you guys to tell me what the population is based on your understanding, and they're different on what, right? I don't want you to say the population is different. Different how? Different what? Again, forcing you all to be thinking more precisely about what we're doing with these analyses. Questions? All right. So what we're going to do, we've made our hypothesis statement. Then what we're going to do is we're going to collect or make a decision on what we're going to identify as a probable or a not probable event. Probability of obtaining sample data, assuming that the null hypothesis is true, is what we use to start to make inferences about our population. Okay. Sample means found to be much different from the proposed population, interpreted as incompatible with the null hypothesis, okay? Or the underlying assumptions of the statistical model. Null hypothesis doesn't tell us which, okay? We're getting close to the end of the class, so your heads are probably swimming. We'll pick this up next week. I can't emphasize this enough. If we get a sample, if we say sample should be 80, right? And we get a sample that's very, very different. Sample mean is different than 80, right? We get a sample mean of 100, right? Within the context of our null hypothesis test, we would say, assuming that the population, or the average cognitive score in the population of older individuals taking supplements is 80. It would be very unlikely for us to draw a sample of individuals having an average cognitive score of 100. Okay, this is the basic framework for the logic of our statistical test. And so this effect, if we're sort of playing by the rules of null hypothesis testing, tells us one of two things. One, either the data, we're going to interpret this as data that's incompatible with our null hypotheses, or two, that our data are incompatible with the underlying statistical assumptions of the model. Okay? We don't know. Our p-value doesn't tell us which one of these things are going on, right? But basically, in layman's terms, this is saying either one, it looks like the population parameter from whatever the population it is that the sample is coming from isn't corresponding to the values specified under null, or two, you've made massive violations of the assumptions of your statistical test, and that's kind of what's going on, right? This is something we can test, right? And we'll want to test and go through to make sure to help us start to rule out. Now it starts to become difficult because we're rarely, if ever, working with random samples, but we can at least say for these data that we've collected, we've ruled out the possibility of gross violations of our underlying statistical assumptions, and so going to give us more confidence that if we find that our sample characteristics are quite different than what we would expect under the null hypotheses, that this may mean that the population from which this sample was drawn has characteristics that are different than what we would expect under the null. Okay. However, if we find sample means that are similar to the hypothesized population mean, we would interpret this as our data being relatively compatible with whatever the assumption was in the null hypotheses. Null hypotheses tells us whether the data are unusual under the null hypotheses, but does not imply that your null hypothesized values are correct. Okay. Number one place we see people get turned up and turned around in this, right? So you've got your experiment, right? You've got sample A and you've got sample B, right? Let's say you've got 20 people in sample A and 20 people in sample B. Sample B is your experimental group, sample A is your control group. So you go through and say, okay, well, did my randomization work, right? Do these samples differ systematically on some important characteristics, age, gender, ethnicity, personality, intelligence, exercise, whatever you're looking at, right? And so you go through and you do t-tests on all of these different things, and all these t-tests fail to reach statistical significance, right? And so what you do is you say, there's no difference in my two samples, right? Or these samples are the same across these characteristics, right? Why is that problematic from a null hypothesis standpoint?
Aren't we like basic stuff on probabilities?
What's that?
We're basing stuff on probability.
Okay.
So it isn't that there's no difference.
Okay, right. My null hypothesis is that the difference between these two things are 0, right? Is the difference 0? Probably not, right? All we're doing with our hypothesis is saying, do we have enough evidence to say, yeah, values under the null are not likely? We're not saying, but the problem is if we fail to reject that, right? If we fail to reject the null hypotheses, we're not saying that they're the same. We're not saying that the mean of group A and the mean of population A and the mean of population B are the same, right? We're just saying that we don't have enough evidence to say they're different, right? And so if we start saying that I ran tests on age and my experimental group, my control group, does it differ in terms of GPA, right? Technically, that's an incorrect statement. What you should probably say is we didn't find sufficient evidence to determine that these groups were reliably different on this thing. We're not saying that they're the same. We're just saying we don't have enough evidence to say they're different, right? And this starts to become problematic in theses, dissertations, research papers, right? When you start saying, oh, I hypothesize that there's no difference between these groups. To actually test that is quite a complex all we can say when we find a null effect is that we don't have enough evidence to say something's different, right? If I'm looking at the relation between X and Y, if I'm looking at that correlation, and I don't find a significant correlation, I'm not saying that the correlation is 0, I'm just saying that I don't have enough evidence to say that it's not, right? And so this starts to become important when you're going through and making your interpretations. Threshold for our statistical significance determined primarily by our alpha level. This is our standard for defining what our critical regions are. And this is going to be our semi-arbitrary threshold for determining at what point we say things are unlikely, assuming the null hypothesis. Okay? All right. Excellent work, folks. Questions before we call it a day?